Yeah, as Matt said, my name's Calvin. I'm a second year PhD student here at the Institute of Astronomy, and I look at the dark universe. So you won't be able to see any of this when you go stargazing tonight, so it's completely irrelevant to anything you're going to see tonight. But I'm hoping with this talk, what I'll be able to do is at least demystify a bit some of the words you might see in pop culture surrounding dark matter and dark energy. And these kind of things that are kind of flagged, but you don't really know what they mean, but they seem a bit mysterious, but you don't necessarily know, as an astronomer, how they operate. And I should say throughout, if you have any questions, just ping your hands up. I've been told to throw this cube at you. It's not solid, it's somewhat non-dangerous, okay? So to start the lecture, what I really want to do is explain the contents of this pie chart. So this might be something that you've seen before, in that we're told that the universe is about 70% dark energy and about 30% matter, and we're told that we don't understand dark energy. And then you can think, oh, okay, well, we sort of understand 30% of the universe, so we're not doing too badly. But then we're told again that of the 30% of the universe that is matter, 80% is dark matter and 20% is regular matter. And we're told we don't understand dark matter. So again, we're told that we understand about 5% of the universe total, but then we're told that this universe, the regular matter is contained in stars, galaxies, and dust and gas, and things that we can see. And any astronomer will tell you that we don't understand star formation, we don't know how galaxies formed, and we don't understand how dust and gas got there. So we actually understand none of the universe. But I'm going to leave those parts, that 20%, that regular matter, for different talks. I'm going to talk about dark energy and dark matter. And specifically, do we need to invoke these things to explain the universe that we see? And the answer is, hopefully I'll convince you, yes. Where is it? Where is dark matter and dark energy? And what is it? And if you have a correct answer to that, then you will have a Nobel Prize. So let me know. Okay? So just to clear a few things up, dark matter and dark energy are not the same thing. So before I go into the specifics, dark matter is likely a particle. It interacts with gravity like all matter. It's unevenly distributed in space. And we actually know quite a bit about its properties, even though we can't say what it is exactly. Whereas dark energy, we're not sure what it is. It's equally spread everywhere in the universe. And it's the mechanism responsible for the accelerated expansion of the universe. I'm going to explain all of that, hopefully, in the next bits of the talk. But the main point to make there is that astronomers are lazy. So they have bad ways of naming things they don't understand. Necessarily, dark energy and dark matter sound like they should have something to do with each other, but they don't. They're only dark because they both don't interact with light. So we don't see any interactions with light for dark matter and dark energy. They're two separate things, just that don't interact with light. Astronomers are also lazy because they worked out how to do one thing and one thing very well, which is measure light. So if you're trying to work out dark matter and dark energy that doesn't interact with light, and the only thing in the universe you can look at is light, you've got a bit of a problem. So if you look at a star or a galaxy or something like that, you might see an emission spectra that looks like this, where there are these little blips due to different elements that make up stars and galaxies, like nitrogen, iron, and silicon. And these can tell you by observations of their wavelength that you see with your telescope versus how you expect them to behave in the lab, the velocity of that star or galaxy. You might have heard the analogy made with an ambulance and the Doppler effect, how when it's moving towards you, it sounds higher pitched, and as it moves away, it lowers in pitch. That's because there's a relative movement of the waves that you get from the ambulance that make the sound. And the same thing is true for stars and galaxies. So what you can do is you can measure different emission lines from stars and galaxies. And basically what that will tell you is how fast they're moving. The main point of this slide is you can make complicated measurements with your telescope to work out how fast stars are moving. And that observation was first made by this very angry looking man called Fritz Zwicky in 1933. And I'm told that the coma cluster you might be able to see tonight, but it was the first cluster of galaxies that this man here sat down and looked at And previously, as I said, he worked out the velocity of the stars. And if you remember sort of GCSE physics, if you work out the velocity of something, you'll be able to tell the kinetic energy, the K in this equation here. And then the U is the mass of the system. So if you can work out the kinetic energy, you can work out the mass of the system. So Fritz Zwicky looked at the coma cluster, said, okay, we've got these stars moving about this fast. Let me just check and see how much matter there should be. And he found that there was way more matter than he was seeing by the luminous emission lines from the galaxies that he was observing. So alarm bells started going off in his head saying, okay, these two observations don't match. And no one really believed him for about 30 years because he was a bit controversial. But it wasn't until 1980 that we had Vera Rubin, who was a very, very famous astronomer, famously snubbed for the Nobel Prize for this observation, who made observations of the rotations, i.e. the speeds, of stars rotating around 21 different galaxies. And what she did was she worked out the velocities of these things, inferred the mass distribution that must be present in these galaxies, and she wrote this really famous line that she said, in order for galaxies not to rip themselves apart with how fast they're spinning by her observations of stars, there's the inescapable conclusion that non-luminous matter exists beyond the optical galaxy. And this was almost accepted overnight unanimously as evidence for dark matter. I think a much better name is non-luminous matter, but for some reason I think people like the BBC like dark matter as sort of a phrase. And since it was hypothesized in 1980, we've been able to make really detailed measurements by taking more and more measurements of different galaxies, the same as Vera Rubin did, looking at the rotation curves, inferring their mass distributions, and being able to work out that basically of the regular matter we see in galaxies, we need about 4 times as much non-luminous matter, i.e. dark matter, so that galaxies don't rip themselves apart. Okay, so what does this tell us? Non-luminous matter exists to make sure galaxies don't rip themselves apart if they're spinning too fast, and it has an abundancy about 4 times of that of luminous matter that we can see. Now, but where exactly is it? So, astronomers are really good-looking people, right? You see these. So you've got, again, Albert Einstein in 1915 told us that any type of matter, whether it be interacting with light or not, should be deflected by light via general relativity. And so this can allow us to infer the distribution of dark matter. Whilst dark matter doesn't emit light, it should be bent by light. So these observations of looking at how light is bent from really, really distant galaxies by dark matter we expect to exist between us and the distant galaxies we're observing will allow us to make detailed maps. So we know that dark matter should exist. We know there should be about 4 times as much as luminous matter, but where exactly is it? And it allows us to draw up this cartoon of where dark matter exists in galaxies. So we see that dark matter halos are actually huge. So this is about to scale. If you think of the classic picture you see of the Milky Way, you have a dark matter halo that's spherical that extends much, much further than the reach of luminous matter. And this model, having matter distributed this way, makes all of our observations make sense in terms of the previous observations that Vera Rubin made and more sophisticated observations that you can make. This model, this distribution of a disk-like galaxy with luminous matter that forms stars, but there's actually an extensive dark matter halo that exists around it. And we infer that by looking at the deflection of light from distant galaxies. So we know that dark matter halos exist. They're much bigger than galaxies themselves. But again, can you put it in a bottle? This was something my physics undergrad lecturer always said, can you actually make sense of it? Can you put it in a bottle? So ever since 1980, Vera Rubin proposed dark matter as a solution to these problems she was seeing. There have been lots of theory papers that have explained what dark matter actually might be. And I think some people might know about dark matter, but they might not necessarily know some candidates which have been ruled out or are possible for the actual identity of dark matter. So first, people looked at the massive neutrinos. So you might be familiar if you look at things, the standard model of physics. So you have all these different particles, and that we can understand, and this is tested really, really well at the Large Hadron Collider in CERN. And these particles down here, the electron, muon, and tau neutrinos, were recently discovered to have mass. And everyone was like, okay, we know neutrinos don't interact with light. We know that they have a mass, so they interact gravitationally. Those are the two things that we need for dark matter. Maybe this could be dark matter. And the answer is actually no. These particles are way too small to be responsible for dark matter. But it got a lot of people excited for a little while. And we have these other things. So you know how I spoke about the structure of a galaxy? We have that disk-type luminous center with extended halo. At the extended outer halo, there was this idea that we had these machos, these massive astrophysical compact halo objects, which are effectively failed stars. We think that when the sun formed, it was a collapse of a massive massive cloud of gas, and that formed the star. But if the sun was about 1/100th its size, it wouldn't have actually started burning. It would have collapsed into a dense ball that didn't emit anything and didn't really do very much. So it was proposed for a little while that maybe dark matter was basically a load of failed stars in the extended halo of our galaxy. Maybe these things just didn't form, we didn't see them. But we should be able to see them via their deflections from distant galaxies, and they'll sort of interact with the light that we see from other galaxies into our telescopes. So we should be able to detect them in a way that we don't. So these were also ruled out. So we've got the two cases here. We've got massive neutrinos, which were proposed. They were ruled out. These massive compact halo objects, we should have seen them. They were ruled out. And then we move to the LHC. So we've got these WIMPs, and you can tell that physicists have really bad acronyms with these weakly interacting massive particles. So we want a particle that's weakly interacting, i.e. doesn't interact with light, that's good. Massive, i.e. has a mass, will interact with gravity, two things we need for dark matter. And extensions to the standard model suggest the existence of more exotic particles. So when I mentioned neutrinos previously and I said that they had a mass, that wasn't expected in the standard model, so we know something's wrong. Neutrinos weren't predicted to have a mass, so we can look for extensions to this model in other places. And at the moment, CERN is upgrading to look for these particles. And if I was to put a bet on what I think dark matter would be, I reckon in the next 10 years we'll have a direct detection via CERN of these particles. But people have been saying it for the past 30 years. And I'm only 2 years into my PhD, so what do I know? Really? So the question mark remains over this as to whether or not CERN will be able to detect a weakly interacting massive particle. Obviously, it's very hard to detect something that's weakly interacting, because ideally you want it to interact. But that's a problem for people in the physics department over there, not us astronomers. Okay, now to change pace completely, when I spoke about dark matter, now we're going to talk about dark energy, which again is just something that we can't see via interactions with light. So on the left here are the original measurements done by Edwin Hubble of stars in the local galaxy. And what he did was he looked at how far away they were. And if you remember previously when I spoke about how astronomers make measurements of the emission line from stars to work out how fast they're moving, he made this really famous plot of the distance away from stars versus how fast they're moving. And he found this straight line. This is the best straight line you're ever going to get in astronomy. This is like the best correlation between two data sets you'll ever see. So he inferred that the further away a star is, the faster it's moving away from us. And to update to the 2000s, we have a huge new wealth of data that basically confirms this prediction. And if you look in the bottom right there, on the right-hand plot in the bottom left, you see this little red square is actually the original area that Hubble looked over in terms of distance. You can see the expansion we've had in the last 100 years in terms of data. So what we have is this expansion of the universe in that if something is further away from us, it's moving away from us faster. So if I tell you that dark energy is basically just a name we give to whatever mechanism that explains this graph. So we know the universe is expanding. That means that the further away something is, the faster it'll be expanding away from us because the space between us is expanding. But I always feel like that's a bit of a cop-out answer when astronomers say the universe is expanding, because you never really have a physical intuition of what space is expanding into. So there's an analogy here. If you were to draw 4 dots on a balloon and then inflate that balloon, and if you lived on the surface of that balloon, you would see all these points get further away from you. But if you weren't aware of the higher dimension you lived in, you would just say that the balloon was, what is the balloon expanding into? But it's expanding into the face that we exist in. The universe is expanding in the same way, but at just one dimensional level higher. And that's really hard to conceptually understand. But if you take it down to this level and think a balloon with 4 points drawn on it expands in this way such that all points get further apart, the analogy holds when you think of the universe and you go to a higher dimension. Okay? But I struggle with that and confused myself when I was making this slide. So don't worry if you guys understand it. So the expansion of the universe, dark energy is the mechanism that explains this expansion of the universe. And you see here this plot that's made with the fit to the previous data that I showed, but then also the fit if you say the universe isn't accelerating. And you can see that that observation is completely ruled out by these observations of stars that are nearby us. So you can see that actually having about 70% of the universe, the energy density that's required to force space to expand at the rate that we see it by observing these distant stars, we can pretty accurately say that we know that the universe is expanding and that expansion is accelerating based on these observations that we make. But if I were to summarize that for you, you shouldn't be happy with that answer, because we actually don't know very much about dark energy. If I summarize what I've told you there, is that dark energy is evenly distributed, because if we look in the sky, we see that the stars are expanding at the same rate in every direction. Okay? If it was clustered like dark matter, then we would see some anisotropies or some inhomogeneities in terms of the expansion that we see. But everything's expanding at the same rate in all directions. It means that empty space must have some kind of energy input to make that space expand and the space between us get bigger, between us and the stars that we see. We do not know what is causing it. We don't have a good theoretical answer. There's some, as I say here, possibly the same energy field that caused the Big Bang, but this is a really open branch of theoretical physics, realistically, not even astronomy at this point, because the maths is so hard in terms of working out a theory that doesn't break every other observation that we see. So if I was summing things up or weighing things up, we could say that measurements of exploding stars show us that 70% of the universe is in dark energy, where dark energy is just the mechanism to explain those observations that we see in terms of the expansion of the universe. Measurements of rotation curves of galaxies, i.e. looking at how fast stars are moving around galaxies, tell us that of the 30% of the matter that's remaining, about 5/6 of it is non-luminous, i.e. dark matter. And we have a good idea or good motivation as to where to look as to what dark matter is. But dark energy is much more mysterious. I'm happy to take questions on that, but I'm not sure I'll have a good answer. And with that, that's the end of my talk. Thank you very much.